office space has evolved to become more open and collaborative, but with that comes the challenge of managing the waste produced by multiple people. This can become a point of inefficiency for janitorial staff, who have to check and empty each bin individually every night. That's where our autonomous trash robot comes in. A Roomba is used as the foundation of our robot. We added additional sensors and computing hardware, including a LiDAR, NVIDIA Jetson processor, and 2 USB cameras. Depth sensing capabilities are provided by the LiDAR, which has a 360-degree view in a plane of its surroundings. Additionally, the Roomba provides odometry data, measuring the travel distance and orientation of the robot's wheels. To create an autonomous system, we need to have prior knowledge of the office space that the robot will be operating in. The robot uses SLAM, a mapping algorithm, to chart out the office using our onboard LiDAR. This results in a map including initial positions of desks, chairs, walls, and other objects. This allows the robot to navigate through the office using its map while determining its position within the environment. The locations of the trash bins are recorded manually after mapping. The map must tolerate day-to-day environment changes, such as tables and chairs being moved. Our robot still needs to navigate through the office and successfully locate bins if this occurs. Our robot uses ROS, an open-source robotics library. ROS supports a navigation framework called NavStack, which provides localization and path planning support. Localization is the process of identifying the robot's location, which uses the pre-made map, LiDAR, and odometry data. This is combined in a ROS package called AMCL that determines our location and orientation when moving around an office. Another package called Global Planner creates a path from the current location of the robot to a goal destination using Dijkstra's, a shortest path algorithm. The NavStack also includes a local path planner, which detects and navigates around new obstacles that were not on the pre-made map. The state coordinator is our central decision maker, keeping the robot on track to complete its necessary tasks. It's implemented as a ROS node in Python and uses a state machine to track metadata and implements the logic required for navigating and picking up bins. The coordinator is responsible for interfacing with our database, which stores bin locations. The coordinator also keeps track of the current bin that the robot is navigating to. To interface with ROS, the state coordinator uses the ROS-Pi framework. This allows it to receive the robot's position and LiDAR scans, as well as send movement directives to the Roomba.
During global navigation, the state coordinator uses the front and rear cameras to search for bins. Each bin is outfitted with AeroCode tags, which are similar to QR codes, and they're easily identified by the state coordinator's vision system as a bin. If a bin is identified and matches the current target bin selected by the state coordinator, it transitions to a local navigation mode. If the bin isn't found, it's recorded as a missing in the database and notifies the janitor, and then another target bin is selected. The first step in docking is orienting the robot's pickup arms with the bin. The robot uses the rear camera to detect the location of the AeroCode tag and uses the provided coordinates to align itself with the bin stand while backing up. Once the robot is sufficiently close to the bin, it uses the LiDAR to measure the distance between the robot and the bin to back up, align, and prepare for a bin lift. The alignment funnel between the arms ensures that small errors in the vision or location navigation systems don't impact our ability to move the lift arms under the trash bin. Once the arms have been aligned under the trash bin's base, the state coordinator commands our stepper motors to lift the bin. The motors precisely drive a gear system that increases the effective torque output, allowing us to lift heavier bins. The outermost gears have circular cams offset from the axis of rotation. This offset translates rotation into vertical motion, lifting the bin off the ground. By doing this, we can move the trash bin around the office more efficiently without sliding it along the ground. A key feature is that we can power off the motors when they're not active, since the cams are in a stable position when fully raised and do not hold weight when lowered. This helps us conserve battery power, allowing the robot to work for longer periods of time. All signals to control the motors are sent from the general purpose output pins on the Jetson and are controlled in software by the state coordinator, which has the authority to command a raise or lower operation. Once a bin has been successfully lifted, the coordinator tells ROS to navigate back to the bin drop-off location. As you can see, part of the LiDAR's field of view is blocked by the trash can. To mitigate this issue, we created a transformation between the original scan and a cut-down scan with a lower field of view. When the robot reaches the drop-off point, the coordinator lowers and then moves out from under the bin, ready for another pickup. Once the Roomba has returned all bins to the drop-off location, the janitorial staff will be responsible for emptying bins and replacing trash bags. When trash bins have been emptied, the state coordinator will begin returning bins to their original locations. Once all trash bins have been emptied and returned to their home locations, the robot can proceed to the charging area.
In terms of testing and evaluation of the robot, we can see that it is performed within the physical constraints that we have set for it. During development, we had to decide between using the Jetson Xavier AGX, which draws more power and is faster, and the Xavier NX, which draws less power but is less performant. We decided to use the NX because of its lower power draw. During testing, the robot demonstrated a battery life of up to 4 hours with constant movement and has proven to be quite accurate in its sensing capabilities, with a 99.6% lidar accuracy and a 92.3% camera accuracy. Although we did not meet our goal of being able to lift a 10-pound load, we were able to lift up to 5 pounds, which is sufficient for most office waste. Given a higher voltage battery, we believe we could meet the 10-pound goal. In terms of docking testing, we measured the success rate at different rotational and linear movement velocities. We found that a linear movement velocity of 0.05 meters per second and an angular velocity of 5.5 degrees provided the best trade-off between docking success and the speed of bin collection. In our integration testing, we found an overall success rate of 80% over 20 trials and found an average trip time of 3 minutes, which is fast enough to pick up an estimated 90 bins in an average office environment over the course of 5 hours, such as in the New York City Meta office. Moving forward, there is still room for improvement and future development. For instance, we could explore the use of more powerful batteries, stronger motors, and an additional IMU, and more efficient algorithms for navigation and control. Nonetheless, we are confident that the robot we have developed provides a strong foundation for future research in the field of robotic trash collection.